talking about, we're in the acid-base section, very long section. I think I see here 24. I think it goes up to somewhere probably around 180, 190, a lot of slides. We've talked about different definitions of acids and bases. I think we talked about Arrhenius's definition. We talked about Brodston and Lowry's definition. And then I think, and you guys can remind me, I started to introduce Lewis's definition of acids and bases. Yeah. Is that correct?
Yeah.
Okay, so Arrhenius's definition, just to recall, is in water, and the formation of hydroxide would be a base. Something that you put into water and the formation of hydroxide in the product, that would create the thing that started as a reactant with the water, a base. Should make sure that's clear. Mm-hmm. And then something that I start with, and then I end with mixing it with water and end with hydronium ion, or H3O+, which also can be defined as just a proton. Right. That is considered an acid. Then we went to Brodsted-Lowry's definition, and that was more broad because there I didn't need it in water, right? There it was just, if I transferred a proton, it's an acid. Mm-hmm. If I accepted a proton, it's a base. Those are the two. The third definition then expanded that a little more. It did not change what a base would be, per se, but it does expand and broaden the definition of an acid, right? And in that context, it was just what? Lone pairs. And what happens with the lone pairs? As an acid, you accept the lone pair, right? So that would be either with something that is deficient in lone pairs, like a couple examples, I think, if you recall from 101, beryllium and boron, they don't like to form octets. So they have that deficiency in terms of a full octet. So that means that they would accept a lone pair. So that would make them acids in this context. Nothing to do with proton transfer, nothing to do with formation of hydronium ion, which are what the other two definitions were, right? In addition, if I had something that was an ion, right? So if I had a cation, then I would be deficient in those electrons, and I would also be considered an acid because I can accept a lone pair from something else. And that's essentially the definition of a Lewis acid. And the base, of course, is just going to be something that donates the lone pair. Right. Okay, so you can say that it donates electrons, right? And the reason why that doesn't change much in a base, because that's essentially what a base was anyways, right? If you think about how a proton transfer or accepting, right? If you're a proton acceptor as a base in Bronsted-Lowry's definition, well, that's exactly what you already have that lone pair. You're just accepting the proton to it. So it's essentially the same thing. Okay. So here's an example. This thing here, Bronsted-Lowry is a proton. Lewis model focuses on the electron pair. Remember, an electron pair that's free, and that's why we're using the definition of lone pair. You can call that a lone pair or just an electron pair. Okay, but it's available. It's available to give off. If it gives it off, if it grabs something from it, it's the base. Whatever it grabs is the acid. That's Lewis's definition. Is that okay? So, Lewis acid, electron pair acceptor. Lewis base, electron pair donor. Different than proton donate and proton accepted. Okay, so to make sure that you're dealing with electron pair versus proton is the difference in those two terms, even though it comes across as the same thing. It sounds similar. So here, all you're doing, here's the lone pair that's being, that's grabbing the electron deficient thing. In this case, it's an ion, and it forms like this. So you're basically taking ammonia plus a hydrogen, and you're forming ammonium. The reason why I don't like this example much is because, in a way, this is kind of just looking like a Bronsted-Lowry, right? Yeah. Right. But explaining it differently, even though it's the same thing in this context, but it does not have to be a proton. This example gives a proton.
Okay. Which one is more common in normal use?
It all depends on what you're looking for. Most common, what did you learn in 101?
The proton.
Arrhenius and Bronsted-Lowry, most common.
Right.
A little more broad, Lewis.
Yeah.
A little less common, but still applicable depending on what it is you're researching. So a lot of this will depend on what it is that your focus is on. Okay. So this is the same, like I said, this looks very much like the process of Lowry. However, I'm using it now in the context of electron donor and electron acceptor. Okay. So this is the Lewis definition, just put in context of what you saw prior with process of Lowry. Which of course then hopefully we get one that's a little different. Let's see. So once again, this doesn't change much the base for the most part,
Right.
but it does change and expand what you would consider an acid. In other words, what would accept, because now it's just not the idea of a proton transfer.
Mhm.
And here's an example of it. So here, so as an acid or something accepting the electrons or the electron pair, this is important because you have to have something that can accept them. So I have a full octet, and I don't have, say, a D and F orbitals and whatever else, or I'm just not comfortable accepting those things. It makes me unstable as a molecule. Then I really need to have something that either is deficient in some way, whether it's naturally deficient in electrons, or if it's already given up electrons to make it deficient and therefore a cation. So that's the same kind of thing I mentioned before. And boron particularly likes to have 6 electrons around it, right? So that means it's lacking 2. So it makes it a great acid in the context of Lewis acids and bases because it's now capable of accepting a lone pair from something else, even though there's no hydrogen associated with it here, right?
Yeah.
And that's what makes the expansion or the more broad concept of
Definition of
Lewis
it,
acids. Because now this lone pair can attach to that boron and form this complex here based on this. Yet there's no hydrogen, no proton transfer, there's no hydronium or hydroxide involved here whatsoever. This is a base in the earlier definition of the Arrhenius, right? In water, this will create, with H2O, it will create OH minus in solution. But in this case, it's not creating any OH minus, it's just donating its electrons, which is the same thing it did before, by the way, to grab the proton. But now it's donating it to something that's not a proton, something that's BF3. So this is still a base, which is why the base isn't really changed much here in terms of definition. But this is now an acid, where before that wouldn't make any sense, because there's no proton. Okay, so that's the expansion. So here's the acid in terms of Lewis, and here's the base, but that would be the same either way.
That formula is just given the example of it, what it looks like. That's not how it's written with the.
Oh, okay, so I think what you're asking is the representation here
Right.
of these 2 dots. Yeah, usually it's just like this.
Right.
But the representation here is showing where the lone pair is coming from, the nitrogen, and what it's interacting with the boron.
Okay.
So that's specific to what's going on in this particular example, yes. I think we should see, so here's your Lewis acid, here's your Lewis base. By the way, I think I emphasized this a lot in 101, but just in case, those of you that didn't have me, when I'm talking about, and this relates to redox, by the way, because I think later on in a later chapter we're going to get into redox reactions and things like that, right, the electron transfer. When I'm asking what is an acid, what is a base, whether any of the 3 definitions, or I'm asking what was reduced or what was oxidized, I'm always looking at the left side here, right?
Right.
Yeah.
These are the things that are happening to. I could never say this is the base
Yeah.
or the acid.
Yeah.
You have to orientate yourself appropriately. You have to understand what you're looking at. You're specifically looking at this and this, forming that. Therefore, this is the acid in this case. This is the base in this case, according to Lewis. I've never defined this as an acid or base.
Right.
Right? In the process of Lowry, I would come over here and say this could be the conjugate acid or base, right? In that context. But I'm always looking at the left side when I'm evaluating this. I always, once in a while, I'll see students and they'll write, I'll ask something like this on the exam, and they'll somehow write this is the base or the acid or something. That doesn't make any sense. That's the thing that's the product from one or the other, and it's only a product as a result of which one of these was the acid or the base. Okay? Just make sure that your orientation's appropriate.
So we wouldn't be looking at something where the equilibrium was switched. We would always be looking at.
So, the question now that's being brought up is, and for good reason actually, because if you think about it, you just took an exam on chapters, the first 2 chapters, I think we call them in the new 14 and 15, and 15, or the second chapter, was all about equilibriums.
Right.
And there's no equilibrium here.
Yeah.
Right? So, so what we're moving towards, right now, all I'm doing is defining an acid and a base in different ways. That's it. We are going to move towards the strengths of acids and bases. When we get into strengths of acids and bases, we're now going to talk about equilibriums with weak ones. When we get into equilibriums, we'll discuss how that factors in. We might even get to that today. I don't know how fast this will get to, but we will get into things with equilibriums. In this case, we're only looking at two things that are creating it, whether or not they're considered an acid or a base, not the strengths yet. Okay? That kind of precipitates another question, actually, which is, in the equilibriums you guys saw, a lot of that was all about chemical reactions, right? With decomposition we looked at. I think we looked at synthesis. Right. We looked at other things. In the acids and bases, a lot of times we're just going to be looking at whether or not that thing, when it's mixed with water, is dissociating or not dissociating, which is different than taking two things and forming a chemical reaction, literally.
Right.
But there are chemical reactions involved when I have something that now, let's say NH3, that pulls a hydrogen from it, from the H2O. I've now taken that and made this NH4 plus and the OH minus. So it's kind of like it, but it's with water. And that's going to be a really important point to keep in mind as we go forward. So we will get into equilibriums, and we probably get into them pretty quickly here, I would imagine. And then, of course, we're going to use what? Ice charts and K for the acid, Ka for the base, Kb's, and we'll get into that. Okay, so incomplete octets, things like boron and beryllium or two, and then anything that becomes a cation will always be deficient in electrons. Anything that has the electrons available can bind. So in this case, aluminum is lacking 2 electrons, boron's lacking 2 electrons here. So these would make ideal Lewis acids because they can accept an electron pair or a lone pair from anything that has it available. Okay. So these are incomplete, therefore they like to form, they like to act as acids in the context of a Lewis acid because they have availability to their positions. Okay, so here's an example of that. So here I'm going to use the NH3 ammonia again with the 2 electrons on the nitrogen, the electron deficient aluminum. This can act as a base by donating this pair. This can act as an acid by accepting that. And then I end up with this structure right here. Okay, that's it. Go ahead.
So, and you don't have a conjugate base or acid?
Not in this context. Only in the Bronsted-Lowry, not in the Arrhenius either.
Right.
So the conjugate acid base is a product of what happens from what would be considered a Bronsted-Lowry acid base pair.
On the product side.
Yes, on the product side. Go ahead, Peter.
Is it a complete transfer of electrons, or is it just now sharing?
Sharing.
If it was complete so two things that you could think about outside, just to give yourself a sense of that. If it was a complete transfer, these wouldn't stay together.
Right.
This would have the
charge. This
would have a charge, that would have a charge. And secondly, it wouldn't start this way and that way. Right? Right. Because these are the more stable versions of them. So the more stable versions is what it's likely going to be. So then there would be no reason for it to completely transfer over because then it would just automatically have existed the opposite way anyways. Just instability, just as a way to think about things. But it's an interesting question, but you see why it doesn't. Yeah. Okay. Now, here's another example of this. Now I'm getting into some bigger molecules, maybe something more, this would be organic or something like that, where I have this thing here, something that you're not familiar with, so we start with something you're more familiar with. Here's something you're not familiar with, and this thing here, without looking over here, what do you think is going to happen? If I'm defining this in terms of acid and base, just looking at the reactants here, what's happening? Boron's electron deficient, it can act as an acid because it can accept a lone pair.
Right.
Where would that lone pair be coming from on this molecule?
The oxygen?
The oxygen, absolutely. So this is what these two things have the opportunity to grab that, making this the base, that the acid, and that's exactly what happens here, as you can see.
Right. Does it create a dipole moment?
Well, the whole thing will have one most likely. I mean, we'd have to look through it, but clearly this side's different than this side in terms of molecular,
Right.
right? But then this looks like, well, this may not. This one has a dipole moment already anyways.
Right.
So in terms of polarity,
Mhm.
this looks polar, this looks non-polar as a molecule, even though each bond
Doesn't
has
make
polarity,
sense,
right? And then this here looks like it's polar just because, remember the simple way it taught in 101? Just look at
Right.
one side and another side. They're different, it's likely they're polar,
Exactly.
right? There's a dipole moment.
Right.
You could have a structure that connects that's not the center atom, right? Like, for example, if you had a much larger molecule, instead of the oxygen, it would be at some other point.
It could be.
Could be.
Could be,
Just all
absolutely.
the examples.
If it's
of
available.
that,
In this
so-
example, there's nothing else that has a lone pair associated with it. You know, and this is kind of cool, when you get into OChem, which is next for you guys, it will be kind of fun because you'll start to electron push. And you'll say, well, if this electron comes down, that may force that out, where this can grab, that comes out. And you could form carbocations.
Mm-hmm.
So these carbons could end up with a positive charge on it called a carbocation, which then would allow it to act as a Lewis acid in this case, because it would accept an electron lone pair because it's not stable. But because it created more stability in another part of the molecule, they'll move around. We might see an example like that just, is there?
There's the light example.
Oh, good, okay. So hopefully we'll see something like that. So these are electron deficient, these are gonna be the acids in terms of Lewis, and then these will be the bases with the electron pair rich, called electron rich. Okay, so the general idea is okay here?
Yeah.
Okay, good. Oh, here, we get to see electron pushing here. So exactly what I was saying here. So here you have H2O and C and carbon dioxide, CO2. Okay? These are this thing and this thing here. And in this case, you don't have a deficient electron region around the carbon. It's got its full octet. Okay? You can see that here in the CO2, right? 1, 2, 3, 4, and that each one has 2, so you have a total of 8 electrons, right? It's got a complete octet. It's comfortable. But I have these electron-rich oxygen on this water here, and that allows us, either one of these lone pairs could attempt to bind the carbon. Of course, that would put an extra pair of electrons around it. So as a result, what the carbon will do, it will then lose, and if you think about this, the electrons on the oxygen-carbon bond in both of them, remember you have the double bond, so you have them in pi regions, and then the sigma region in the middle, right? Those are the orbitals associated with the molecule. So they're going to be closer, though, to the oxygen because the oxygen is more electron negative than the carbon. So that allows for this to come in here. If it can make that contact, one of these bonds could then go up towards the oxygen, forming 2, 4, 6, and a single bond here. Carbon still has its 4 connections, or its 8 electrons. But that means that this oxygen here is a little less stable. It could lose these 2 electrons here, while this pair can pull off the hydrogen, and you have this whole thing called carbonic acid, which should look familiar to you.
That activity that's happening is not related to like the resonance, right? The resonance structures?
No.
Okay.
Resonance is you think of resonance on its own.
Right.
One molecule and different conformations that particular molecule can have. Here we have 2 different molecules interacting with each other, reforming positions of things so that the whole thing is more stable at the end.
Okay.
Okay, as opposed to one thing being in different ways.
Right.
Okay, that's important. So what I started with was water and carbon dioxide. What I end with is carbonic acid. And that's exactly what happens in OChem, where you start to do the electron pushing and surrounding, and you'll get names for these. And then you'll be able to anticipate what should happen if you start here and you end up here. And you'll be able to do the mechanism. And this is basically looking at a mechanism to how some of these conformations occur. As opposed to just putting up H2O plus CO2 and arrow, and I get, right, H2C, what is that, H2CO, CO2 or something like that.
So this would be far less common than having, let's say, a carbon that doesn't have its orbital full, right? Because it seems like it would happen less if the carbon's already stable. So the two oxygens that are, or the two electrons that are coming from oxygen, like, I don't know, it seems like a harder reaction, like it would take longer or something.
Let me make sure I'm clear on what you're asking. So you could be asking about the speed or the rate, the kinetics of this, or you could be asking about the specifics between the two things interacting.
Those specific two things, like because carbon already has its octet, why would it take more? Why would that also?
So then the second, then based on that, it depends on what carbon's connected to. So if carbon's connected to another carbon here, then that's highly unlikely. But it's connected to oxygens. And oxygen can then do this and pull that hydrogen off where another carbon couldn't do that.
Okay.
So it depends on what you're looking at. In this particular case, these are very functional groups, these oxygens here, because of the double bond and because of their availability to do this kind of thing. But if I exchange this for, say, a fluorine, that's not going to happen there. You see, so
Oxygen's way more electron negative too, so the electrons are gonna be closer to the oxygen than the carbon.
yeah, but then it would be with fluorine too, but that wouldn't happen with fluorine.
Right.
It's very, it depends on what you have there, and what we'll call, in 101, last semester, I think I had after some chapter, did I tell you guys about organic chemistry a little bit, just functional groups?
Yeah, definitely.
These are the functional groups.
Right.
Functional groups meaning that they're more willing to do reactions
Right.
because they have availability in terms of, or I should say flexibility in what they can do, whether or not form this double bond, come up here and then grab that hydrogen. That's something an oxygen can do that maybe another functional group wouldn't be able to do, let's say, or something that wouldn't be considered a functional group like carbon. So that's the whole point of the functional groups in organic chemistry. When you identify what they are, then you can see that they can do a variety of things, and then you'll learn more specifically what those things are. That's essentially what one section of OChem will teach you. Okay, but of course, what I'm showing you here is just looks, two-dimensional. In OChem, you're going to learn three-dimensional, so they're not all going to be sitting in the same plane. They're going to be in the full scope of a three-dimensional plane where they could be on one side versus another, or the same side, cis versus trans, and where their position also matters to whether or not they can do this. Okay, so that's stereochemistry that you'll look at in OChem. But for our purposes, this is just to give you a sense of what kinds of things can go on in these interactions between what I'm defining here as a base and this as an acid. Okay. I hate this example. Because you can't really, there's no way I could walk you through how this works. All I'm going to say here is that this is going to act as an acid, as a Lewis acid. Why? That would be the first question, because this is exactly like a multiple choice question, right? Because it's electron deficient. That's how you should think of it. So a lot of the questions that some of you missed on the exam is the same kind of thing here, where you just didn't identify the core of what it was asking. And the core here, if I ask something like, what happens in this thing, you would have to say, well, this is electron deficient, that's why it's a Lewis acid. Yeah. This is electron rich, that's why it's a Lewis base. Right? Now the odd thing here why I say that is because then I take this plus 6 of these and I form this kind of thing here. How does that happen? I can't just, there's no knowledge that you have now that would explain why that happens, other than it's more stable. Because why 6 and not 5 or 3?
Yes.
In fact, your instinct should say it should be 3.
Yeah.
Because you have 3 positions available here, 3 plus, yet you have 6 that are actually binding.
Yeah.
This is just called out, this is a coordinated covalent bonding pattern that deals with crystal fields theory, which means that if you look at it from the bigger picture, like for example, from a molecular structure, not just an individual thing, then it becomes more stable this way. Once again, the difficulty there is you've only seen up to tetrahedral as far as I know, right? So this doesn't make tetrahedral, that's more than, hence the crystal field theory, where you get up into things with octahedrals and stuff like that. Which we're gonna actually get into, I think, this semester. Did we do octahedral? We did do. So you can get a sense of that then.
Yeah.
Why would this be, say, octahedral?
Oh, you
It
got
has
the
to have
four-
d orbitals, right?
Yeah.
Okay. And where is it here? It's in group 3. So could boron do that?
No.
It'd be a little harder for it because it doesn't really have those unoccupied. But without knowing that, all you really need to know is this is acting as a Lewis acid because it's electron deficient. This is acting as a Lewis base because it's electron rich. Hence you get this. But we will get later on into coordinated covalent structures that deal with metals as the center atom. And then it creates these kinds of weird structures here. We'll get into that a little bit, a couple chapters from now.
Trigonal as well.
Okay, but like I said, for now, all you need to know are these two things. Okay, we finally done with, okay. So here's just a way to look at all of these Lewis acids, electron pair acceptors, usually positive ion or electron deficient molecule, and Lewis bases, electron pair donors, usually negative ion or a molecule with lone pairs available for some kind of interaction. Because of course, in a three-dimensional structure, and once again, just like 101, I'm showing you very small molecules, right? So imagine bigger ones, like in a biological system. It'd be a little harder for these things to interact. And why would it be harder for them to interact? Orientation, right? And number of times they connect in that proper orientation. And that was all wrapped up in what?
Into A.
Into A. As P and Z in A, right, from Arrhenius' equation, right? Which is all part of what?
UK.
K,
Right,
all
K.
the constant. Yeah, absolutely. See how these things all unfold.
Right.
It's kind of pulling you back and reminding you.
For the last slide, were you talking about, like, with the center atom as a transition member, you're talking about, like, complex ions?
Mhm.
And stuff like that?
Mhm. And they're bound covalently coordinated.
So, like, you just,
We'll get into that. So what that is, I mean, basically, since you're asking again, when you really think about this, all I'm doing is putting an aluminum ion in water. But then if you really think about what I'm saying that the water then interacts with the aluminum in a certain way,
Mm.
as opposed to just saying that the water is sitting here separately from the aluminum.
Mhm.
That's all I'm saying. So literally you have water surrounding and making bonds in what's called a coordinated covalent bonding pattern with the aluminum.
Hydrogenation.
In other words, all the things that in the past I just called them aqueous.
Right.
They're actually bonding patterns if you look at the thing that's aqueous relative to the H2Os that are sitting there. That's what we're going to move towards a little bit later. That helps. That help a little bit?
The hydrogenation.
Yep. So neutralization is just a reaction in which electron pairs are transferred so that you have a bonded pattern. They're not a plus and a minus, it's not completely transferred. They're just saying that they're transferred in a way that forms this binding. As opposed to the formation of water, which is how you knew it before, just to make sure that that's clear. Right? A little different. Lewis acid base is completely different than what you've learned up to now. Is this a Lewis acid or base? Acid, right? Electron deficient. What about this one? Base, electron rich. What about this one? Acid, electron deficient. And this one? Base, electron rich. Okay. So, acid, base, base.
Right.
Okay. Okay, no, I guess I want to do a quick comparison probably between the Lewis and Bronsted to show, all this is really going to show is what you already know. Maybe I'll move through this a little fast, but the basic thing here is that the base is kind of the same and the acid is slightly different. So a Lewis acid, Bronsted-Lowry, you have a base here, has the electron rich, the lone pair. Here you have a proton. The proton is transferred from the acid to the base. And then here you get your
Conjugates.
base, this is your conjugate acid, this is your acid, that's your conjugate base. Okay. The similarity of Lewis, once again, the base is almost exactly the same, except for now the acid doesn't necessarily have to have an H associated with it, but it doesn't have to.
Right.
That's the only difference. And so now you're just transferring presumably not literally transferring, but you're
Lone
taking
pairs.
these electrons and you're transferring it over here so that you
Yeah,
have
so-
this balance here.
And there's no conjugate acid.
No conjugate
Lows,
acid.
yeah.
Because it would be the same thing.
Mhm.
It'd be, the conjugate acid and the conjugate base would be for both those two.
Right, liquid molecule.
Okay, so, we're gonna look at it again. Okay, so here's just another version of the same thing. Here they are representing this as a positive and a negative, but that's not, I guess let me make
Kind
sure
of
I
give
don't
you
have
respect-
anything, that they don't have anything in the exam like that. They are saying here that it's a positive, it's really not. They're just being shared.
You should just have the lowest dot,
Yeah,
right?
yeah.
And they just
Here,
make
this
that
is
one.
absolutely true. They're being transferred there. Here, they're just trying to show a similarity to it, and they're not really transferred. That's the problem. It's just sharing it.
And just telling you the
Yeah.
polarity.
Yeah. In other words, if I put this in water, they don't separate into ions.
Right.
I put this in water is separated in ions. That's what I mean by transferring.
Oh, you got that bond.
Yeah. Big difference, yeah. Take note of this. I'll make sure when I make this exam, I gotta remember to make sure that I don't have an old, when I juxtapose the multiple choice, that
Mhm.
there's not an old answer on there that indicates something like this. And if it does, then it will make sure that there's nothing else that could possibly be right, and you just use it. All right. All right, now, okay, so now we're gonna transition. Now we've defined acids and bases. Now we're gonna look at acids and bases as strengths, strong or weak, okay? Now we're just looking at those differences here. So if you recall electrolytes, you had the strong electrolyte, weak electrolyte, non-electrolyte. That basically meant that if I put something in water, it separated completely, it was a strong electrolyte. Not specific to acids or bases, just in general. So I put an ionic compound in, and it separated, then it's a strong electrolyte. If it partially separated, usually very little separation, then it was called a weak electrolyte, because you had few ions in there. And then if it didn't dissociate at all, it was a non-electrolyte. Okay. Now I'm going to apply that specifically to acids and bases. If I have an acid or a base that separates completely, then it's called a strong acid or a strong base. If I have it separates partially, then it's a weak acid or a weak base. That's it. Nothing overly, intellectual there, right? It's simply if it separate, and what I mean when I say this kind of thing, so let's say I have HCl and C2H3O2. So I have acetic acid and HCl. And if I put a certain concentration, the same, 1 molar and 1 molar, same amounts, and I put those into water, this all becomes H plus or H3O plus Cl minus, right?
Right.
All of it.
Yeah.
So that means 1 molar, 1-to-1 ratio, I get 1 molar of this.
Right.
If I put this one in, I get something like this where I have only some of them forming like this and some of them forming like this. And of course, using ice charts, which is what we're going to get to later, then I can figure out exactly how much of this and how much of these I form. So let's say I only have about 95% of this, only 5% of this forms. That means 5% of this 1 molar is this. So if this is 1 molar here, because it's 100% dissociation, over here, it's only what, 0.05 molar.
Right.
Weak acid, I have few of these. Strong acid, I have a lot of these. That's the essential definition. Same thing would be for a base. Okay, does that give you a sense of what that is? Of course, I could end up, what if I put in like 100 molar? Not possible. Let's say I have 100 molar. And then I get this partial, well, yeah, I might end up with a lot of these, but overall it's still very few compared to like a 0.0001 molar. In other words, I could also dilute this a lot where I barely have any of these as well. I'm only looking at them if I'm putting the same amount in at the same time, or 2 different containers. What else do I want to say here?
So what you're starting with make a difference, it's what basically is going to help you to define what is it going to be. Like once you find, like using the ice chart, you're going to find like the constant.
The second thing I wanted to bring up here is the strength here means that this interaction here is strong or weak.
Strong.
Strong. Well, actually, weak. Yeah, weak.
The opposite.
Right. Like
This
a strong
is a weak
electrolyte.
interaction makes it a strong acid.
A strong electrolyte.
Right? Yes, because it will separate easy in water. This here doesn't separate much, so it's a weak acid. Is the connection strong or weak? Strong.
Weak electrolyte.
That's the other thing I wanted to point out, because that's tricky, right? You think of strong, strong, weak, weak, everything's got to be, no. In this context, if I'm saying this is a strong acid, it's because I'm making a lot of these, and this connection is weak. Okay, so make sure you keep that in mind. And there's one more thing I wanted to point out here. The second thing here that I want to point out, actually, this is interesting. So this is strong, meaning I make a lot of these. It also means that whatever remember, I start here, I now have 0 of this once this is complete, and all of this. So that if I have the concentration here, the concentration just runs through the balancing of it.
Yes.
Okay? So that means if I have 25 molar of this, 25 molar of that, 25 molar of that. Just to make sure that's clear, right? So then, if I'm determining concentrations, whatever I start with should be easy to find what I end with. I also don't have a what? There's no equilibrium, there's no coefficient. There's coefficients in the balancing of this thing, but there's no Kc or whatever else,
No, okay.
right? Because it's not an equilibrium. In this one here, there's an equilibrium. So here, if it's 1 molar, I can't say that's 1 molar. In fact, I'm only estimating 95 at 5. At some point, I want to figure out what this is. And to figure out what this is, I'm going to use the ice charts. Okay, and then we'll know exactly what I have here. And here, I do have an equilibrium constant. So if I have an acid, I'd call it Ka. If I had a base, I'd call it Kb. So those are the things I want you to know about strength. So in other words, if I had something like this, what do I call that? What's different about that top one than these two here? They're 2 protons, so this is called diprotic. This is monoprotic or mono, because these don't count because they're not acids. These don't come off as H's because they're connected to carbon, which is too strong of a bond, so they're not coming out in water. Okay. So in this case here, would I call that strong or weak? Strong.
So strong,
And why was the why was that strong?
You don't let go of 1?
Because there are 2 more oxygens than hydrogens.
Right. Oh, yeah, I did.
Right?
Mhm.
All right, let's check. There are 4 of these, 2 of these, so 2 or more oxygens makes it strong.
Right.
So the first one's strong. So the first one would go what? All the way here to this. Right?
Mhm.
But not all the way. 1 arrow, no equilibrium. But now here, can that also be an acid? Is that one going to be strong or weak?
It's gonna be weak.
That's going to be weak. Every subsequent hydrogen that comes off is going to have a harder time coming off because it's now tighter in that complex, right? So that makes this one a weak acid, but it can still come off. But if it's a weak acid, is it going to form a straight arrow or this?
The equilibrium.
This.
Right.
So then from here, I'd have to figure out what that percentage is off of something like that. So I'm giving you a preview of all the things that you should be thinking about as we move forward with strengths, okay? So that it's not just,
You can also have, can you have 2 equilibriums back to back? Like your initial has an equilibrium, and then your product in that case would have another equilibrium.
you mean the first hydrogen coming off and then the second and then the third? Yes, possible. That would be the first one would be weak. Where would we see that?
Bicarbonate?
It's H, what is that, H2CO3, yeah?
Mhm.
Yeah, also phosphoric acid,
Phosphoric
H3PO4,
Right.
right? That's only 1 more oxygen each.
Carbonic?
So, And then you'd have to figure out, now that's interesting though, because at some point I'm gonna have a certain amount coming from the first one here. It's gonna be a lot more than I'm gonna get off the second one.
Right.
Then what happens? This is kind of cool. Think about this actually, I like this. This is fun.
Exponentially smaller enough.
So this is my first one, and now I'm gonna pull this one down And by the way, this is strategic. This is really important, what I'm showing you, because it is going to matter to how we do things later. Right?
Yeah.
Those are the two, in this case. So if I'm making a bunch of this and some of this, how is this affecting this? And what's the overall amount here? You guys, this is stuff that you learned this semester.
If you're making a bunch of what?
You make a bunch of hydrogen, you're gonna want to push it.
Yeah, Le Chatelier's principle. I have so many of these, the few that form here, it's going to come back and shift it back that way.
Yeah.
So I'm going to have even less coming from here. Think about this, kind of cool, right? This is all stuff you guys learned this semester.
Yeah.
And then if that's the case, then most of what I'm getting is here, this might even be negligible. You might not even want to include it, depending,
Yeah.
right? Depending, each situation could be different. This could end up where you have only a few of these, so few that I have, say, 1,000 of those and one of those. Do I really want to say 1,001? Same thing as 1,000, right? Depending, situations will be different, but these are ways to think about how you're breaking up this into these two things. And remember, each time I'm just adding water here, right? And now if I put aqueous here, that assumes you already have it from here. Okay, so these are some of the things I want you to start thinking about as we move through, because that will help you understand now that you have the bigger picture. As I break it down, hopefully it will help understand a little bit more about what's happening and why some of these things are occurring. Okay, so this is just a simple thing about electrolytes. I think we talked about weak, partial, strong, dissociates, whatever, right? That shouldn't be a problem. Here, once again, just to remind you, single arrow means complete ionization. You could also say dissociation. Some people will get particular in how they state it. I really don't care. The idea is they separate, however you want to define it. Right, separation, obviously they're going to go into ions, so that's hence the ionization, same thing. Just a fancy term for that, for separation. Okay? And that's a strong one. So this is all stuff you know. Here's a list of some strong, basically for strengths, and this, I think I did this in 101, let me just reemphasize it since we're getting into it now. You have binary acids. So the binary acids, hydrogen with either fluorine, chlorine, bromine, or iodine, over here in column 7. All of these are strong except for the fluorine, which would be the one you would think would be the strong one because it has the greatest electron negativity difference. But because of the way it intramolecular interacts with itself, makes it harder to pull those apart from each other and therefore harder to pull out the hydrogen from the fluorine. So the only one of those 4 binaries that are weak are the HF. Everything else, HCl, HBr, HI, are all strong. Pretty simple for binary.
Yeah.
Right.
For anything that's an oxyacid, usually bound to a polyatomic, right? And therefore an oxygen. If you have 2 or more oxygens per acid hydrogen, so there's 3 here, 1 there, that's 2 more, then it's strong.
Right.
At least the first one if it's monoprotic. Diprotic, if they're 2, the second one is going to be weak. Okay. So here, 4 oxygen, 1 hydrogen, that's more than 2, 3 more, this is strong. 4, 2, the first one is strong, diprotic, meaning 2 of these, but the second one would then be weak.
Right.
Just to give you a sense of how to determine strength of an acid. Go ahead.
So if it's weak, it doesn't completely dissociate?
That's right. If it's weak, it doesn't completely dissociate. You're always going to have the double arrow. Absolutely.
So if there's 2 or more hydrogen on it, then it's considered strong.
Depending on the oxygen.
No.
Depend on the oxygen.
If I have a ratio that, or let me rephrase it. If I have oxygens and acid hydrogens, if I have 2 or more oxygens than the hydrogens, then it's a strong acid. So there are 4 oxygens, 2 hydrogens, 2 more oxygens, so that's 2 or more, that makes this strong. But once I get rid of the first one, I only have 1 left. The second one is always harder to pull off and will always be weak. And if there's a third, if it's triprotic, like H3PO4, then the second and the third one. And you would imagine the third one is probably negligible to the total amount of hydrogens coming off. And you have Le Chatelier's principle kind of working against you there too.
You can have
Right,
the-
so that's going to minimize even more the, how much you're going to get out of the first 2. Okay,
Sulfurous acid would be weak.
what's that?
Sulfurous acid would be weak.
Say that again?
Sulfurous?
Oh, sulfurous acid. What,
Yeah,
what do you have there?
sulfurous.
H2SO3?
H2SO3, right.
That would be weak.
Right.
As an acid. Not as a breakdown into what?
Into electrolyte.
Into,
Into ions.
it's an unstable intermediate, right?
Right.
So it breaks down into a gas and water off a
Okay.
double, yeah. You just brought up a unique case, I just wanted to be clear about that.
Right.
Right?
Yeah.
Okay, so those are strong. Here, weak, you have HF, that's the only one. And that's only because, once again, it's not because, so traditionally you would automatically assume HF is going to be strong because it has the greatest electron negativity difference between all of the binaries in the column 7, right?
Okay.
But it itself binds intermolecularly, in other words, HF binds other HFs that are associated with it or adjacent to it. And it forms hydrogen bonding patterns because a small electron negative atom, nitrogen, oxygen, or fluorine, binds to the adjacent hydrogen, forms hydrogen bonds, which is a pretty strong, if you recall, intermolecular interaction. And therefore, it's hard for the water to separate the HFs from the other HFs. That's why it's hard, not because if you had a dilute amount of HF, where they weren't not that many were bound to each other, so they were surrounded by the water, it'd be a strong acid because they'd all separate. But because of the way they interact with each other through intermolecular interactions or hydrogen bonding patterns, it's hard to pull those apart so that you could then pull off the H.
The concentration matters.
So then, the determination of whether it's a strong or weak acid is by how diluted it is? In this example?
No, in this case, you're just going to call it weak. It's just weak. You're going to assume you're putting in a certain amount. You're not going to. I'm just giving you that you could adjust the situation by doing other things, right? But in any situation we're going to come across, we're going to assume we have enough in there, and therefore it's weak. And it's weak for the reasons that I just brought up. Not because traditionally you would expect that to be strong. Sure. Right. Okay, so that's all that is. Okay, I like this is interesting. So remember here I said 95%, 5%. I think in 101, I always said, oh, it's somewhere like 95, 5. Everything was 95, 5, made it easy, right? Since we weren't actually figuring it out. Because we didn't know ice tables or equilibriums at that point. So I couldn't really tell you a whole lot more. But some may be 4% or 4.2% versus 96 point something percent. Some could be 50% and 50% or 40% and 60%. Who knows what it is, right? So the degree that it may be strong or weak, well, strong is pretty obvious, it goes 100%. But the degree to which it is weak will depend on whether or not you have how strong that binding pattern is. The same thing I talked about earlier, right? So it's a competition. So in this case, the SO4 is competing, or the HSO4 is competing with H2O for that hydrogen. So if the H2O can outcompete this, that's a strong acid because a lot of that comes off, which means that this is here a weak bond. Or strong bond. Weak or strong?
Weak.
Weak.
Right.
That's what makes it a strong acid. That's the thing I talked about earlier. Right? Over here, this thing is now connected, and this is actually literally connected to the oxygen, and H2O is now competing for this one with this thing, right? This thing and H2O are competing for this. If it's weak, that means that this thing is binding it stronger than the H2O can bind to it, and therefore not as much comes off.
Yes.
That's all this is saying. That's all this statement is. The
Right.
attraction between the anion of the acid and the hydrogen ion relative to those with water. It's competition. If it's a weak acid, that means that the H2O is winning that competition. If whatever's connected to it's winning that competition. If it's a strong acid, then the H2O is winning that competition.
Right.
And that's all that's really happening there. Just getting more particular about it. So this is the same kind of thing. All right, we can maybe move through some of this a little faster. Same thing, strong attraction, partial ionization, weak attraction, complete ionization, strong acid. So I like this. Okay, so here you can say strong acid, weak attraction between whatever it's connected to. Weak acid, strong attraction between whatever it's. And then of course that means partial ionization and complete ionization. So you have it all wrapped up right there. In case you get confused, go to this slide as you're studying and then put it in context. Because think about the multiple choice questions I can ask associated with this, right? And think about how twisted, it's almost like saying a tongue twister, right? Where you say like something over and multiple times and then you start like getting it confused on how you say it. thinking about this over and over, like it starts to get confusing, especially if I create a way to state it that would be easy for one person and confusing for another. Take this little picture, associate these things all together. In other words, you can't put this here. You can't exchange these terms. All of these stay together, all of that stays together.
Right.
However the question is asked, make sure that you're looking at this one or this one in relation to that question. That's all I'm saying.
Like that.
That's an easy way to wrap it up and avoid confusion. If you just try to float it around in space in your head and kind of like, I kind of have this here and this kind of associated with this, and then all of a sudden on the question that's not as straightforward, it doesn't simply say if it's weak, is it strong attraction, right? It says something more confusing. You can kind of like take this and just pull it all together and then answer that question. If it's free floating, the answers kind of become free floating. They all start to look right. Right? I mean, I've done the same thing. That's why I'm able to say that. We all make these kinds of mistakes, and then how you adjust and create a better system for you to hold it all together will dictate a lot of times your grade. It doesn't mean you know more than the other person. It just means that you were able to condense it all and put it in the proper context. Okay, CL, blah, 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 reverse reaction. Okay, same kind of thing, okay. So here are 6 weak acids now. So the weak acids, once again, no big deal. I have 2 oxygens, 1 hydrogen. That's only 1 more oxygen, must be weak. 2 to 1 must be weak. The HF's the only binary weak. Here, 2 to 3. Diprotic, the first one's weak, but the second one's even weaker. 3 to 2, first one's weak, second's weaker. 4 to 3, first one's weak, second one's weaker, third one's even weaker. Okay. Have I explained in this class why the second one would be weaker? Okay, maybe I should just, that's a good place. So as opposed to just, some of these things that I've skipped, by the way, skipping over doesn't mean you shouldn't read them maybe, but I've already talked about them. So there's no reason for me to read off the screen. It doesn't add any value to what you're doing here. But what I can do is something like this, where let's say I have, let's do the simple one. So I have C, C, H, 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 double bond O, O. That's no good.
Oh, you sprayed it with the phosphoric, wasn't it?
I need something like this. Hold on. That won't be any good for this one. S, O, 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 O. Okay. Now, I'm not going to do the complete Lewis structure, so some of these might be double bonds and stuff like that. Let's assume those 2 are double bond. I'm not 100% sure the interior here in bonding pattern is right, but that's not what I want to point out. We could do this with the Lewis structure, by the way, figure this out. Here and here. What I'm pointing out is these are the 2. So this is H2SO4. So I have H2SO3 on here, but now just pretend this is H2SO. So H2SO4 has 4 oxygens and 2 hydrogens, which means it's a strong acid.
Right.
Okay. Where that one would be a weak one. So this I have H2O here, and these 2 things, and these things are really grabbing this, which then causes that to fold in. Right? This first one's strong, this is a weak interaction here, so it pulls that away, and now I have the negative charge there. Okay. This is a strong acid because this one comes off. Now this is what's left over. This is HSO4 minus, right? And what happens here? So I already have the electrons between these 2 things. Oxygen is higher up than S, so they're favoring here. Okay. This happens, I now have a lot of electron density over here because this, even though this was being favored over here from here, it was still being shared.
All right.
Now it's all the electron density is on the oxygen,
More affinity,
which means that some of these things now will start to shift a little bit closer to the sulfur than where they were before. And if these are shifting to the sulfur a little bit more, what happens here? These will also shift a little bit closer to here. Meaning that these ones will now shift a little closer to here, making that one harder to pull off. Just to give you a sense of what's happening. That's why the second one's always harder than the first, and the third would be harder than the second, because you're tightening up the connections and making the electron density is now trying to disperse itself to different areas, where before it was separated in a certain pattern. Once the electron density gets more in one area, then it tries to release some of that stress throughout the rest of the molecule, which then over here becomes more electron density towards here, making these more equally shared, and that, of course, much harder for the next, H2O to pull off.
I'm trying to bind it right.
So that's why it becomes stronger, a weaker acid, the second one.
Can you explain what happened to with the hydrogen in the water again?
Yeah, what did the water, how did the water want to take another hydrogen?
Liquid iron.
Hydronium ion.
Right.
Becomes a hydronium ion. Okay, so that gives you some sense here, and then the rest here, this should be based on how we define the strong, the weak should be pretty obvious. Okay, so now, when we're looking at the formation, we have an acid, and now we've just formed something, or we've caused one of the hydrogens to leave, which is why it's an acid, strong or weak or whatever. If it's strong, do I have a constant?
No.
Right, no. I don't have an equilibrium constant.
Right.
If it's weak, then I have an equilibrium constant in the formation of that acid. And I just call it Ka instead of Kc. No big deal. Same concept. Okay. So here I'm just saying Ka is the equilibrium constant for a weak acid.
Is it only going to be aqueous instead of gases this time for KC?
What do you think?
Aqueous.
Yeah.
Yeah. So I don't know if you guys recall, I think when I started this, I think I said it was odd how we did the equilibrium constant, but
The gases, right.
because most of them are in gases, and yet we were calling those concentrations,
Right.
right?
Partial pressure.
That's why we did the partial pressure, because that makes more sense with the gas.
Exactly.
Yeah.
But it was really to set up for anything aqueous in the acid-base reactions, to use the ice charts and
Concentrations.
the equilibrium constants was really designed. We did so much of that in the context of Kc for the acid-base reactions. Because those are usually not gases, those are usually going to be in the context of a solution, right? So Ka, so I have this thing here, Ha, this is going to be this is a generic acid. It's clearly weak because of double arrows with the H2O, and I get this and this, right? I could state this either way. I could either have the H2O here and the H3O plus here, or I could just say Ha aqueous and then H plus, so I get rid of the H2 and the H2 on each side. Either way is appropriate. What's actually happening is this is too unstable. It will really bind to this. So this is the real situation that would occur in a solution, but this is an appropriate way to express the same thing, just to keep that in context. Nothing really new from what you've learned in the past. And of course, this is for weak acids. So based on that, I could create the Ka either from the top one, which would be here, or the bottom one, which would be here. And the only difference, of course, is the H3O plus or the H plus. Why is that? Because the water's a liquid, so it's already constant, right? As we discussed in equilibriums. Good. So you got to carry over your knowledge here. So anything that's aqueous or could be in a concentration that has that flexibility in terms of what it would be. That goes in the constant. That goes in the equation for the constant. Everything that would be very
Solid.
little, or unless it's some extreme circumstances would change, then it would be wrapped up in the constant already.
Like solids, liquids.
Solid, liquids, gases
Gases.
would not be. Only solids, liquids, gases, and aqueous would be in the Ka in the expression,
Right.
just like before. And of course, Ka is essentially what? That's just Kc.
Right.
Right, just keep that. It's just for an acid. For a base, it would be Kb. And so that would be if I had something that translated to a base here, then it would be Kb.
Is it also weak base?
Yes. Well, and why? A strong base would be what?
It dissociates.
It dissociates completely.
Right.
Yeah, like KOH with water would just be K plus OH minus, one arrow.
Right.
No equilibrium. Maybe I should state that more regularly. This is an equilibrium constant, is Ka, just like Kc. That where it's specified. Maybe that helps, because then you know if you don't have an equilibrium, you don't have a constant.
Right.
Yeah. By the way, just because I say you don't have one, does that mean you don't actually have one?
No.
No, could it be really, really small?
Yeah.
Yes, I think we might explore that a little bit later. There are some things where you put them in water, just like that aluminum example, where that formation could be very small, and then you would still have an equilibrium constant if you have them going in both directions.
That's why it says the strength of an electrolyte depends on the extent of dissociation.
The
yeah.
extent of it, yeah.
Right.
Yeah. We assume a lot of times, and I'm showing you things that say 100% dissociation, not always 100% dissociation.
Right.
All right, let's see where we are here. So here, okay, so they jump right in. Okay, so just like equilibrium constants, you obviously have equilibrium constants for acids, for Kas, right? And they're set up the same way. So it's exactly the same concept we learned with equilibrium constants, whereas if you have a high one, it favors what? The product or the reactant? The product. If you have a low one, it favors the reactant. That's it. So since it's weak, most of them are going to favor what? The reactant, right? But having said that, can there be different degrees of that? Yes. And that's what you see here. So you have chlorous acid, down hydrofluoric acid, benzoic acid, acetic acid, phenol. You come through here, here's your Ka. This is 1.1 times 10 to the minus 2. This is 6.5 times 10 to the minus 5. Which one has greater ionization? The 1.1 times 10 to the minus 2 or the 6.5 times 10 to the minus 5?
Yeah,
This one has the greatest, what?
Ka.
Ka, which means what?
90%.
It ionizes more, the greatest ionization. So this is a stronger weak acid than that, is what I'm saying. Does that make sense? These are all weak acids. I got to make sure that's clear, because if it was a strong acid, it wouldn't be on here.
Yeah.
You wouldn't have a Ka. So these are all weak acids, but this is a stronger weak acid than anything below it.
Okay.
That's essentially a better way maybe to say it and put it in the proper context. Okay? So a decreasing strength going down this way, which also means increasing what? The interaction between the acid and whatever it's connected to.
Okay. Then to get the percentage, you compare it to the initial?
Say that again?
Your K equilibrium of the acid, to get the percentage itself as to how much it will be.
So if you're asking about ionization percentage.
Right.
So if you take an ice chart and you figure out what you have at equilibrium of your acid and then of its conjugate base, you take the conjugate base, divide by what you started with, times 100.
Okay.
And that would tell you your ionization.
Nice.
Okay, we'll get to that. I think we do have some things where we do that. Oh, sorry, Dieter?
Can water potentially have a Ka too? Since
Absolutely. So water is amphiprotic, right? It could act as an acid or a base. So in its capacity as an acid, when it gives off its hydrogen, it would have K. You think it'd be high or low?
it would be
Well,
low, right? Because
Probably pretty low, right?
Yeah.
It doesn't really want to give up that hydrogen very often.
right.
But if you have something that's ready to pull it off,
Then it goes this.
yeah, then it can, absolutely. Okay, so what do I have here? For this reaction, determine, really? Okay, so first what is the acid, what is the base here? What side am I looking at to determine that?
Okay. then let-
Yeah, 102, you guys are good enough, right? 101s, they start telling me this kind of stuff. I'm like, how is that an acid or base? So over here, the
Nitrous
one that
acid.
gives off the hydrogen, so we're looking at more traditional sense of Bronsted-Lowry. We could also think of this almost as Arrhenius if it's in
Arrhenius,
water. So I have, this is gonna give off the H to form this, so this is my acid, this is my conjugate base. This is going to accept that hydrogen, so this is the base and the conjugate. That part should be easy. Okay. Now, it says, and their relative strengths. Which one's a stronger acid or a stronger base? Right, in this case, let's just say stronger acid. So which one is stronger in terms of the acid? The NO2 minus or the CH3CO2 minus? Now you see what I'm looking at, right?
Okay.
So which one prefers to hold the hydrogen? When I say it that way, well, this is a weak acid here. Which one is the acid again? This one?
Right.
So which one, as a weak acid, is this side favored or is the Ka going to be greater than 1 or less than 1? Let me do that. Less than 1. Because these are gonna have a lot more of it than this, most likely.
That would be stronger.
Which means that the NO2 is much stronger interaction with the hydrogen than the CH3CO2. Do you see how I broke that? And you see why that's a tongue twister. It's a brain twister. You got to keep all these things in the proper order as you think about them.
Yeah.
And it will still take you a minute to think about it, but that's exactly what some of the test questions are like, right?
Mhm.
They're not intended to be that way. They just are because of what the information of the material is, right? So I broke this down saying that this is my acid, this is my base, this is a weak acid, which means that this interaction's pretty strong. The Ka should be much less than 1. It should favor this. Now, what can I do? I can go over to the other side. I could look at this, and I could look at this. So I have HNO, what was that, HNO2?
Yeah.
HNO2 and CH3CO2, okay. So HNO2 right here.
Mm-hmm.
So this is whether or not it's a strong or weak, and the other one was CO3,
CH3CO2.
CH3CO2. That would be this one, right? So that would be this. So this one looks like it's weaker if you look at it this way. It's decreasing in terms of its strength to give it off. So you would expect, so what we get here, we conclude, let's do this here. There's your conjugate. This is this stronger acid. This is the weaker acid in comparison to these two here. This is the stronger connection, though, you would think here. If you go there, so what happened here was, this is actually flipped. So that brings up a whole different point that I should point out here. Okay? That is that when I have the equilibrium, does it matter which one I put in the front or the back?
No.
The left or the right? Alex, for you, does it matter which one goes in the first or the second? I ask that for a very important reason. When you're thinking about this, how do you think about it? Go ahead. If you were going to do an ice chart, let me rephrase this. Okay. What would you? How do you determine what you put in there? Is it based on the concentrations? So if I give you the initial concentration of this one and not of the other one, how would you make your chart? Would it go with that one first and that one second? That's what you did on the exam, and you were right. But what you did was, in my opinion, you made it more complicated. For you, you made it easier because it worked. And that's why I'm asking you. In other words, you can, no, in other words, you can do things more than one way, and I want you to express yourself. I want you to be able to think about it the way you are, and you can get it right. That's perfectly appropriate.
Mm-hmm.
But what I'm getting at here is that I could put this on this side and that on that side. Does it really matter? They're equilibriums.
Right.
The assumption is that because these are on this side, that's what I started with. Does not necessarily mean it's the case. If I let this go, if I start with this, and then it forms equilibrium, then that's usually what you're looking at. But in all fairness, I could just mix the two, either these two or those two, mix it up, let it form equilibrium, and I could write it any way I want after that.
Right.
Right? Everybody follow along there?
Yeah.
So if I did that, then let's assume I did that. Now I don't know I started here. I now don't know, since I don't have the Ka here, I really don't know
What's your product?
which one is stronger or weaker.
Right.
My original assumption was that this one is how it started, therefore this should be a stronger interaction because I should have more of it over here than over here. But after looking at that table, it's the exact opposite because of which one has a weaker, a higher or a lower Ka. This one had the lower Ka, which means that this is a stronger interaction and therefore a weaker acid than this one. Yet in the direction it's shown, if you assume that you start with this, then you would expect the opposite. Everybody see that? Keep that in mind. There's a little bit tricky there. The assumption here was not to make the assumption that you started there, and that's why I mentioned Alec. He actually would put it the opposite because he's more comfortable starting with a number as opposed to 0. Right? And so that's kind of an interesting, in other words, you can look at it either way. Okay, so this would be the strong base, and that would be the weak base. Let's try another one. I have this here. So which one's the acid over here? This one, which one's the base, and then that would be the conjugate base and the conjugate acid, or the conjugate base, the conjugate acid. and we come over here and we say, yeah, it's a base. If we're starting, by the way, in this context, I'm starting on this side.
Yes.
You have to start somewhere.
Yes.
Right, conjugate. Now, let's take a look at HCN and this other thing over here. So I have HCN, where I have it here, HCN here. So HCN is going to be weaker than whatever that other thing was, if it's on this chart. This one?
Yeah, formic acid.
Okay, so that means the strength of this is weak, which means that you have a stronger connection.
Yeah, but weaker acid.
So this one would be your stronger acid.
Right.
That would be your weaker acid.
Cool.
Does that make sense?
Yeah.
Now, once again, in the base part here, we didn't evaluate the base. We're evaluating the base based off the acid, just to keep that in mind. We're going to get to the whole base section later, or at some point in this chapter. Okay, what do I have here? Hydrogen oxalate ion is amphoteric. So amphoteric means that this could be either an acid or a base.
Mhm.
That's the term amphoteric, okay? So that means that this H could come off, or I can add another one to it. Right, the balanced chemical equation of how it reacts as an acid towards water or base. Okay, so I basically take this, I put it together. Well, this is weird because this should be, this should only be -1 here, I think. This is wrong. This should be a minus, not a 2 minus. Should match that. I mix it with water, and I'm first making it act as an acid. So if this is acting as an acid, it's giving up its hydrogen. So over here it's forming H3O plus. That's losing the hydrogen, so then it's C2O4, now 2 minus. Make sure you write your notes say -1 there. Do that? This is, okay, so then that's, okay. So this should be -1, this should be 2 minus. And then as a base, I do the same thing. I put this with water, and what happens? It pulls the hydrogen off the water, and over here, I get OH minus plus H2C2O4 uncharged. That's just it acting as an acid or a base. Okay. Now, I don't know why it has the double arrows here. It's not necessarily relevant here because it's just asking you, it's not telling you it's weak. It's just saying it can act as an acid or a base, and here's how it does in the context of water. Okay. Usually something amphoteric, though, is weak on its own. That's why it's able to do both. If you have something weaker than it, then it does one thing. If it has something stronger than it, it does the other. Go ahead.
So there was a question like this on the test, so it wouldn't matter if we put double arrow and just one arrow, it was similar.
Let me make sure I say the right thing. Write a balanced equation showing how it reacts. I would say if it's amphoteric, you should write the double arrows because you could presume that it's going to be weak for both.
Okay.
That just means that the reason it's amphoteric is because, remember, it's in a competition. So if it's competing with something, then if it can go both directions, it's probably somewhere in the middle. So it could outcompete something in one way, and then it can't outcompete other things in the opposite way. So I would say put the double arrows because it usually implies that it's not strong. If it's strong, then it's usually not going to be amphoteric. It's only going to go one way, right? So that's what I'm suggesting here. Yes, put the double arrows, even though that's not implicit in the thing. I would put the double arrows, even though I might not take off if you put a single arrow. Sometimes I'm just looking, do you get the concept that it can go both? That it does this reaction here and that reaction there. But you should put both for the reason I just mentioned. Okay.
Which is basically all we got there.
For each acid below, right? But really? Okay, this is a Chem 101 guy. This must be a leftover. This is.
I'm crazy. I'm looking at it, I'm like, how else are you supposed to do it? Is this supposed to be harder?
Yeah, they're supposed to get progressively harder. This is like, I think this is a mistake. So let's make sure we know what this is. So the conjugate base of this is? PO4 3 minus. Okay, good. We're all, okay. So let's have more of them. Let's just skip them. What is this one? Same thing, but really? So this is for each base, show, write the formula. Conjugate acid of this, let's just do one. Yep, right.
Minus.
Okay, so that's good enough. Let's move through this. Waste of time. Okay. Anybody not clear on this, you can ask me for the answers, but this is something. if you don't know this, you probably have no idea what I've talked about up to this point today. It's implied that you knew this in order to understand most of the things I've talked about. So, and if you don't, that's okay. Just come to me and I'll work you through it. All right. Okay. Now let's real quick before we wrap up. Let's just quickly talk about the auto-ionization of water. I'm only going to have you just know the basics. I don't want you to derive anything, even though if you're interested, I could show you how it's all derived. Basically, this is water is amphoteric, so it could act as an acid or a base. In this case, it's acting as a base because it's pulling out the hydrogen from a strong acid. In this case, it's acting as an acid because it's given up its hydrogen or proton in order to form ammonium and hydroxide. Okay. By the way, you notice in this case here it's strong, but that's because this is strong. This one's weak, and that's what's dictating the double arrow in this case. So it doesn't always have to be what I said before, which is why I paused on that, and I probably wouldn't take off if you just did a single arrow. It also depends on what it's interacting with. It'll depend on if it's strong or weak, and that's what I was implying and suggesting that usually it's in between, so it usually will form, but in this case it didn't. Right? Okay, so if I have water with just water, so in other words, pure water, but the other implication here is I have something in water that's causing this, right? But if I have just a pure substance, just water on its own, I have H2O and H2O, can't distinguish, and one of them could give up a hydrogen and the other one could take it. Might not happen often, but that's called auto-ionization. It's just doing it to itself, and then you have H3O plus and OH minus.
Is there anything that makes that happen, or is it
It's
like
just the constant interactions, and you have the lone pairs, and if it organizes, if it moves the right way, you have enough energy,
Yeah.
then you're going to have some of that occur. It won't be a lot you wouldn't expect,
Yeah.
but you have some. There'll be some level of it, and we'll just briefly discuss what that level is. So this is the reaction itself here. Of course, it goes back and forth. So based on this, you get a Kc of this. And I'm going to call that Kc, Kw specifically towards the auto-ionization of water. That's the W. And of course, the Kw in this case would just be this thing here. Right? So it's just the ion product. So ion, H3O plus and hydroxide minus, product, they're multiplied, constant. That's Kw. And Kw is always the same because it's only based on pure water. Right? So it's
No matter how you change concentration,
right.
it's still going to cancel out
Right,
the same.
they're going to cancel out the same. So it's 1.0 times 10 to the minus 14, at least at 25 degrees. Let's assume that we're always going to be at 25 degrees. Right? Because if I move it up a lot, then I change the energy content, or reduce it a lot, I change the energy content. I'm going to either get less of that or more, depending on the energy I put in. So this is in pure water. So that if this is the case, then that means that this is equal to that, the concentrations of both ions. And if I break it up and take the square root or whatever of this, I get 1.0 times 10 to the minus 7 molar. That means in pure water, you always have 1.0 times 10 to the minus 7 molar of hydroxide ion and of hydronium ion, which overall gives me a Kw of 1.0 times 10 to the minus 14. Okay. You can derive these, not necessary. And why I'm introducing this and bringing this up, because this is what's going to lead to the pH system. And in that system, you'll see that this is neutral, right? This is at pure water. If I put something in and I adjust this up or down, then it changes this, and therefore you change whether or not you have an acid or basic system.
So like bleach and stuff.
Yes.
Okay.
That's how you determine basicity or acidity in a solution. But these numbers are kind of difficult, right? You're looking at 10 to the minus 14, 10 to the minus 7. So then we'll put it in the logarithm form, and that will put it in a simple system of 0 to 14.
Yeah.
And that's the pH, and that's why we make the adjustment, right? Just to put this all in context. Once again, you could derive these things, but I'm not requiring it. These are the numbers. The textbook probably has a little side thing that will illustrate it if you're interested, but I won't hold you accountable for that. Because you'll forget it next semester anyways, but you'll always remember this. And this is all that will matter. That's why I don't care. So neutral solutions, these things are equal, and you get that. In acidic solutions, the H3O plus is greater than the hydroxide, and therefore you get something like this. And this would be less than that. And in basic, it would be the inverse.
Vinegar is not too low, right, from water?
Vinegar is going to have a higher hydronium concentration than hydroxide concentration. because it's actually acidic acid that's
Right.
making the vinegar. I think it's at about 5%.
Right.
Yeah.
So, but that's the only, that and water are the
Mhm.
only two things. So it's adjusting it, you would get this increase, this would increase, that would decrease.
Right.
Okay, so let me just, I want to get through this real quick in the last couple minutes, just so that we don't have to pick this up on Tuesday, right? Because this is kind of easy stuff, and I kind of want to, I don't think you need too much of this. This is just another way to illustrate when you have the H3O plus and the OH minus at 10 to the minus 7, this is concentration. Then you have a neutral solution. When your hydronium concentration is greater than the hydroxide concentration, this is an acidic solution. And when the hydroxide concentration is greater than the hydronium concentration, this is a basic solution.
Cool.
Whoops. So you see the acidic, neutral, basic. Okay, no big deal. That shouldn't be any big challenge. Let's just do one of these problems before we go. Oh, yeah, I forgot about the test. Shoot, 'cause we're not getting anywhere. Okay, okay, let me stop this here.